You're sitting on a rock, spinning around a star, drifting through a galaxy that's 100,000 light years wide. Now imagine trying to cross it. What if you could go faster than light? Would you explore distant worlds or accidentally break time itself? Because if you move too fast, the universe stops making sense. The universe is big. So big, in fact, that even saying it's unfathomably huge doesn't quite do it justice. Our galaxy alone stretches over 100,000 light years across. That means even if you traveled at light speed, it would take you over 100 millennia just to cross the Milky Way. And that's just one galaxy among possibly 2 trillion others. But here's the cruel cosmic twist. While we can observe distant stars, dream of alien civilizations, and fantasize about faraway planets, we are stuck in our little corner of the universe by a stubborn law of nature, the speed of light. It's a universal speed limit written into the very structure of reality. But what if we could break it? Could we unlock a cheat code to explore the stars, to visit distant civilizations, to whisper across the galaxy in an instant? For generations, science fiction writers and many physicists have asked the same question. Could faster-than-light FTL travel really be possible? Could warp drives, wormholes, or hyperspace tunnels ever become more than just imagination? But here's the twist. FTL travel might not just be hard. It might be dangerous. Not just physically dangerous, but logically dangerous. Because it turns out that if you go fast enough, you could break time itself. Let's explore why. Faster-than-light travel is one of humanity's oldest space dreams. We look up at the night sky and wonder, could we ever go there? Not just send signals or robotic probes, but actually be there, to touch alien soil, to orbit a distant star, to explore the unknown, not over centuries, but in our own lifetime. Right now, physics tells us this is impossible. According to Einstein's theory of relativity, nothing with mass can move through space faster than light. But interestingly, that rule only applies to objects traveling through space, not to space itself. Here's the loophole. The universe is expanding. In fact, some galaxies are moving away from us faster than light, not because they're flying through space, but because space itself is stretching. This raises a thrilling possibility. What if we could manipulate space the same way? That's the idea behind the Alcubierre drive. First proposed in 1994, it imagines a spacecraft sitting in a bubble of space-time. Space would contract in front of the bubble and expand behind it, carrying the ship forward like a surfer on a cosmic wave. Locally, nothing breaks the speed of light, but from the outside, the ship would be moving incredibly fast. Then there are wormholes, tunnels that could connect 2 distant points in space almost instantly, like folding a map and poking a hole through it. But all of these ideas face colossal obstacles. They require exotic matter with negative energy, more energy than our entire sun, and most dangerously, they may lead to time paradoxes, which could unravel the logic of cause and effect. Still, the dream persists, because when we imagine the stars, we imagine not just looking at them, but going. In physics, causality is everything. It's the golden rule of reality. Causes always come before effects. You flip a switch, and then the light turns on. You drop a glass, and only then does it shatter. This is the fundamental rhythm of the universe. Actions lead to reactions, not the other way around. But what happens if something breaks that rhythm? That's exactly what faster-than-light, FTL, travel or messaging threatens to do. Not in the dramatic Hollywood get-in-the-DeLorean kind of way, but through something far sneakier and more dangerous, relativity. Let's walk through a thought experiment. Imagine two stars, Earth and Vega, separated by dozens of light years. One day, a massive star near Vega goes supernova. Earth detects the blast of light, traveling at light speed as expected. Now, if we had only conventional communication, Earth could send a warning message to Vega at the same speed. All very normal. Cause precedes effect. But let's add an FTL communication system to Earth. When Earth sees the supernova, it sends a warning to Vega using this instant message system. In Earth's timeline, everything seems fine. The explosion happens, Earth sees it, Earth warns Vega. Vega gets the warning before the light from the supernova even reaches them. Imagine a spaceship cruising through space, not faster than light, but close enough to it that the rules of special relativity kick in. Let's say it's moving at 90% the speed of light. That's incredibly fast, and at that speed, space and time start behaving differently from the perspective of the people on board. According to Einstein's theory of relativity, when you move that fast, time literally slows down for you compared to someone who's standing still. That's not just science fiction, it's been tested. Atomic clocks flown on high-speed jets tick more slowly than those on the ground. But it's not just time that warps. Your perception of space also changes. And most crucially for our story, your understanding of what events happen at the same time shifts completely. Now let's revisit our scenario. A star near Vega goes supernova. Earth sees the explosion and sends a faster-than-light message to Vega to warn them. In Earth's timeline, this is all very logical. 1. Supernova happens. 2. Earth sees it. 3. Earth sends the warning. 4. Vega receives it. But for the crew on the fast-moving spaceship, their frame of reference is tilted because of relativity. When they draw their own timeline through the universe, events appear shuffled. To them, Vega receives the message before Earth sends it. Yes, seriously. They're not imagining it wrong. They're not broken. It's just how relativity works when you're moving near light speed. Time slices tilt, and what you consider the past or future depends on your motion. From the ship's point of view, an effect, Vega receiving the message, happens before the cause, Earth sending it. It's as if you saw someone catch a ball before you threw it. This isn't just strange, it's dangerous. Because once you allow different observers to disagree about the order of events, you open the door to causality violations, and with those, you risk breaking the universe. In their frame of reference, Vega receives the message before Earth sends it. Yes, you heard that right. The effect happens before the cause. Now, suppose the crew intercepts the message and sends a reply to Earth in something like, "Turn off FTL transmitter," also via FTL. In Earth's timeline, this reply arrives before the original message was ever sent, so Earth gets told, "Turn off command," and obeys. But wait, if Earth never sent the message, how did the ship receive it? And if they never received it, how could they reply? This is the infamous grandfather paradox. You've created a situation where an event prevents its own cause. The result, the entire chain of events collapses into contradiction. Reality becomes inconsistent. Causality is broken. And the universe doesn't just dislike that, it fundamentally rejects it. Because once you allow effects to occur before causes, logic itself begins to unravel, and with it, our ability to understand anything at all. This isn't just a bug in the system, it's a fatal error. So how do we deal with this? One option is to say, FTL is impossible, and one of the greatest minds in history, Stephen Hawking, agreed. He proposed the chronology protection conjecture. The idea? Nature has built-in rules that prevent time travel, that every attempt to create a paradox will be thwarted by some physical law, like a safety net beneath the trapeze of time. In fact, Hawking's own work hints at a solution. Remember the Alcubierre drive? It turns out that within such a bubble, Hawking radiation, a quantum effect, could build up to extreme levels, destroying the bubble before anything could go wrong. It's as if the universe is saying, nice try, but no. Still, without a full theory of quantum gravity, we can't say for sure. We're missing the bridge between Einstein's relativity and the quantum world. So, with all these time-bending paradoxes, is faster-than-light travel truly doomed, or is there a way to make it work, safely? Some physicists think there might be hope. They suggest that FTL systems could still be possible, but only under strict limitations that prevent paradoxes. For instance, what if we allowed messages to travel faster than light, but only in one direction? No replies allowed? Or maybe FTL travel is safe as long as no one is moving fast enough relative to the sender to flip the timeline. These are speculative rules that could, in theory, preserve causality. Yes, it feels like a cosmic workaround, like placing parental controls on the universe, but it might be the only path forward. The alternative is far riskier. Accepting that paradoxes are real and trying to build a version of physics where effects can happen before causes. That would mean rewriting the logic of reality from the ground up, a monumental task that may prove impossible. So while the door to FTL isn't completely closed, it's not wide open either. If we ever do walk through it, we'll have to tread carefully, very carefully. The deeper we look, the more FTL seems like a cosmic mirage, always just out of reach. And maybe that's for the best, because if there's no FTL, we can't cheat. We can't skip to the good parts. We have to earn our journey across the stars, not in a single lifetime, but as a species, across generations. FTL may be a fantasy, but space exploration isn't. It's just slower. And maybe that's what gives it meaning, because real exploration, real discovery, isn't about shortcuts. It's about persistence, patience, and purpose. So here's the question. What if time wants to protect itself? Could our universe be hiding secrets not just of space, but of chronology itself? If that idea sends a shiver down your spine, then you'll want to watch our next video. Something strange happens when you follow Einstein's math. Because reality might be weirder than you think. Stay curious, stay bold, and keep venturing into the vast unknown.